Hi, in today's tutorial we are going to detect 120 different classes. We will detect breeds of dogs. Let's see the result. We are running an inference on our training. As you can see, this image that I downloaded from Google detected as a Doberman dog. Let's try another image. As you can see, it's also detected as a Shih Tzu dog. We will load the dataset and we will convert the dataset from an XML format to a Yolo format and then run a training over this dataset. So let's get started. Let's start with installation part. Very similar to my previous videos. You should start with open command prompt under Anaconda, an Anaconda command prompt, and then create a new environment. Let's name the environment Yolo v8, and it should be based on Yolo 3.8. It can be higher, but I prefer that if you are doing the same tutorial, choose Python 3.8. Then you should activate this Conda environment that it would be your current environment. And the next step is installing PyTorch, and you should go to the website of PyTorch, and before downloading the right version you should type on your command prompt mvcc ---- version, and this is how you can find your CUDA version. My CUDA version is 11.8. You can be in another version, not really important. If you're not using NVIDIA, you should download the CPU version of PyTorch. You should go to the PyTorch website and search for PyTorch, and here in this is the main page, but this is how you can download the last version. Copy this command if you would like it in the pip command. You can copy the command in Conda command, but I prefer to go to install previous versions and then search for your CUDA version. For example, this version, which is 2.3.1, support CUDA 11.8. It also supports CUDA 12.1, and if you go to previous version, you can find that there are some PyTorch that support earlier version of the CUDA. So basically, after choosing the right version, I decided to install the PyTorch 2.1.1, and this is the full command for installing it with support for 11.8. After this process, you should install Yolo 8.1. You can install a higher version, but if you would like to get the same results, install this command pip install Ultralytics 8.1.0, so you will install the 8.1 version. And there is another Python library that you should install for this tutorial as well. After the installation, let's move to the dataset. I will leave here a link for our dataset. This is the link. It's on the Kaggle website. Of course, all the code, all the installation, all the instructions will be part of the video description. So let's go for the Stanford dataset. And first of all, you can understand that this is a big dataset. It contains more than 20,000 images, and we have 120 dog breeds. So there are many classes and many images. And if we go down, we can see here that this dataset is composed of images folders, and all the images folders contain subfolder. For example, this subfolder is a Chihuahua dogs. So all these images are Chihuahua images, and if we click here, this is a specific Chihuahua, this is another Chihuahua dog. Let's go to another subfolder. For example, this is Shih Tzu dogs. So but I'm looking for the annotation. The annotations are here. So the annotations are divided in the same concept. There is annotations, annotation, and then the subfolders. For example, in this Chihuahua subfolder, if I click here, this is the annotation. This is the annotation for the first image. But please notice the annotation is in XML format with a specific structure. Contain the name, contain the dimensions of the image, the name of the class, and this is the bounding box. In this specific image we have only one dog because we see only one bounding box. Maybe there are images with several dogs that you may find, and this section repeats itself as the number of the dogs. So we have a challenge of converting this structure, this XML structure, to a Yolo format, and I already prepared a code for that. So we will cover the code. We will not type it on the fly. We just cover the content, understand it, and after we understand it on one image, we will run the code for the whole folder and create this Yolo annotation format. So let's download all the data. I already downloaded it, and let's see it here on my local machine. So as you can see, we have dataset, Stanford dog dataset, and here we have all the images. These are all the images. This, for example, is specific dog, and this is another dog named Stanfordshire. Okay, this is the dog. You can see that all the images are in different sizes, different dimensions, so we will probably resize it during the training. And here also we have another subfolder named annotations, and it contains all the annotations for its specific category, its specific breed. Just to see it, as you can see, this is the annotation in an XML format. In this step, we would like to create a code that will help us later to convert all the XML format to a Yolo format. But as for now, we would like to run it on one XML file. So this is the code. I will leave a link for all the code in my YouTube description video. But let's go to the last line. So this is the main target. We would like to build a function that gets a JSON file or JSON file path, and another value for the target path in a Yolo format, and of course all the classes, all the 120 classes that are available for this dataset. So in order to do that, let's start from the beginning of this code. As always, I will leave a link for this code in the video description. So we will start with import OS. OS is a module which provides functions to interact with the operation system. Then we define a directory path where all the dogs dataset annotations are stored, and this is the folder containing the XML files for each dog breed. And next we are initializing an empty list to store the names of folders found in the directory. Each folder corresponds to a dog breed. Then we run a loop through the directory, checking each item. If the item is a folder, its name is added to the folder names list. Next, we initialize another empty dictionary to map the breed names to the indices. And next, we run another loop through the folder names, and for each folder name, extract the part after the hyphen, which corresponds to the breed name, and then store the breed name as a key in the dictionary with the corresponding index as the value. Then we will print the result. Next, we are importing the element3 module from the XML E3 library to help parse the XML files that contains the annotations for each image. Then we'll define a new function, a very important function. This function is convert the XML annotation into a Yolo format. So this function takes the path to the XML file, the path where the Yolo file will be saved, and the class indices mapping as inputs. Here we parse the XML file to extract information about the image and the object in it. Next, we will retrieve the width and the height of the image from the XML file. It's important for converting it to a Yolo format. Then we are opening the Yolo output file for writing, and then we will run a loop through all the objects, dogs that found in the object. We will extract the class name, and we also look for the class index in the breed using the class indices dictionary, and then we extract a bounding box. So this is the bounding box, these 4 values. Extract the bounding box coordinates minimum, maximum, x minimum, y minimum, x maximum, and y maximum from the XML file. Now we convert the result of these box coordinates to a Yolo format. This involves normalizing the coordinates retrieved to the image width and height and calculating the center of the box. Then we'll create a line. We create a line in a Yolo format with the class index and normalize bounding box coordinates and write it to the Yolo file. And this is the running part. Here we specify the path for a single XML annotation file that you want to convert to Yolo format. And here we specify the path where the converted Yolo format annotation file should be saved. And we also check if the folder, the labels folder exists and this specific path, and if it doesn't, we will create it. And this is our main function. This converts the specific XML annotation file to a Yolo format using the convert XML to Yolo function. After this will work correctly, we will jump to do it on all folders of the dataset. But first, let's run it on one annotation file. Okay, this is all the classes, all the 120 classes. Let's go to our subfolder, and this is the file that has been generated. Let's open it, and now as you can see, we can understand that this image has only one dog, one image, and the dog is class number 8. We can go back and see what is class number 8. If you go back here to the list, so this is 0, 1, 2, 3, 4, 5, 6, 7. So class number 8, when we are starting from 0, is this dog. We can see here by the name of the annotation file. So it was stored here. It's the same class. So everything seems okay. So our class is number 7, and this is the folder. It's the same class. So I believe this code works, and we are ready to display this image with the annotation. The next part is displaying the result. So this is our image, and this is the Yolo file that we converted in the previous code. Let's first of all run it, and then we explain the code. Okay, so this is the image and this is the class name. So as you can see, we have a bounding box and we have a text, and this is a Yolo format. And let's explain this code. So the first two lines are the image and the annotation file in a Yolo format. Here we define a dictionary mapping breed names to the corresponding class indices. This is all the 120 breeds. Then we create a reverse mapping from class indices to breed names, useful for converting Yolo class indices back to breed names. Then we read the image from our specific path using OpenCV. We grab the dimension of the image, the height and the width. Then we are opening the Yolo annotation file in a read status. We are not going to write anything, just read the information. Now we initialize an empty list to store the parsed annotation, and here we loop through each line in the annotation file, which represent one bounding box annotations. In our sample image we have only one object, and we extract we first of all split the line into values, class index and bounding box, and the bounding box coordinates, and then we extract the class index and the bounding box coordinates here in this line. And at last we append the extracted values as a tuple to the annotation file. Then we run another loop. We loop through the annotation list to process and draw each bounding box in the image. We unpack the annotation tuple into label bounding box coordinates and convert the Yolo class index to corresponding breed name. And next we convert the Yolo bounding box coordinate relatively to the image size to a pixel coordinates, and here we will draw a bounding box. We will draw a bounding box which is a rectangle around the detected object using the calculated pixel coordinate. And we also add in the label name, the name of the dog breed. We will use the put text to do it, and we will put the text above 5 pixels above the bounding box. And at last we display the image using the IMShow of the OpenCV library. In this part we prepare all the data information, all the annotations in all the folders to a Yolo format. In our previous code we display how to convert only one annotation file. So basically all the first part of the code is the same. As you can see, we define the function convert XML to Yolo, and it's pretty much the same as we done so far. From here, this is the new part, and I will explain it. What we are doing here, we're not only converting the data to a Yolo format, but we also splitting the data to train images and labels and validation images and labels. So first of all, we are creating an output folders, one for train images, next for validation images, and one for train labels and for validation labels. If the folders are not exist, then we are creating them using makes deals. And next we define the source folder containing all the images that would be copied, and here we are defining another variable initials a counter for splitting images between training and validation sets. Now this is the list all folder names in the source image directory, and here we run a loop through each folder in the source image directory. Inside the loop, for each of those folders, we grab the list of images and we run a loop through each image in the list. Then we determine whether the image should be in the validation set or the training set based on the counter. We split the data. Every 10 image goes to the validation set, and all the rest, the 9 rest images, would go to the training. So basically 90% of the images would be trained, and 10% would be validation data. Next, we copy the image to the appropriate directory, and then we generate a Yolo formatted label. From here, we are generating the annotations in a Yolo format. And at last, we're running the convert from XML to a Yolo format, and then we increment the counter and print the current file number. So let's run it. As you can see here, this is the files, and let's go to the subfolder. There is a dataset, and as you can see here, there is a train and there are images. So all the images are copied here, and all the corresponding labels copy to here. And we are changing the names of the images by this numerator. So the process has finished. As you can see, it transformed more than 20,000 images. Let's go to our subfolder. So we have a dataset, and inside the dataset we have train and validation, and inside of those we have images, and we have labels in a Yolo format. Let's go to the validation as well. We have images and we have labels in Yolo format. Great. So now we can continue to the training part. So before starting the Python code, you should create this data YAML. It contains the full path for our training images, the one we have just created, and the full path for the validation. And here are all the 120 classes name. It also should be part of the data YAML. As always, the Python code and all the instructions on all the configuration files will be in the link in the video description. So let's create now its step number 5, which is training. And let's start from Ultralytics. We will import Yolo. Define a main function. Let's load our model. Yolo V8 N. We will use the N. N is for nano. The Yolo V8 has several models. The nano is the smallest one. There is nano, small, large, extra large. So you can read the documentation. We will try the nano one, and we have to add .yaml. This will load the Yolo V8 nano model. Then we have to define our config file. Config file path This is our YAML file, it's here, so let's copy the path for this file. So this is the data YAML file. Just change the direction of the slashes. Yes, let's continue. And now we have to specify the output directory for storing results. So we are storing results. We should name a project name, and let's put it under our dataset. So let's copy the full path for our dataset. So this is the dataset. You can choose your own folder for storing. I will store it under our dataset. So this is the project, and we also have to add experiment. Let's call it experiment name, and we call it nano model. So for each run it will create a different experiment name, nano model 1, 2, 3, etc. Then we define the batch size. And now train the model. Model.train. We have to send several arguments. The first one is the name of the config file. Then how many epochs? Let's try it with 100 as a start. Project should be our project name. Project. Next, the experiment name. And next is the batch size. And device is, if we choose 0, it means the first GPU card. Next, patience is how many epochs we would wait for early stopping. So if there was no improvement in 10 epochs, it will stop the training. So we will wait for 10. Then image size, it will be 640. This is the standard for Yolo v8. Verbose true for login, and val true is to use during the training also the validation data to compare the results, check the results. And at last we have to run our main function. If it equals main, then we can run the main function. And it should be here. We have to indent it here, because this is the main function. It should be outside the function, outside the def function. Great, let's run it and see the result. Okay, load the model. Now we're expecting it to load the images. Okay, let's load all the 18,000 train images. You can see we have one corrupted. It's not an issue. Now we're expecting to load the validation images. It's loading 2,000 images, validation images. And let's wait for the first epoch. The training has started. So now we can see the first epoch. We can see the progress. I believe in this progress it maybe will took 1 hour, 2 hours. So what we are going to do is stop the recording, and we will start once again after the training will be finished, and we will cover the results of this training. So let's stop for now, and we will continue after the training. The training has finished, and you can see here for all of these 120 classes, we can see what are the results for each of the parameters. So what is for the precision for bounded box, and etc. And basically, let's go to the result folder. We store everything here in this subfolder. So we have to go to dataset, nano model. So let's open our dataset and nano model, and first of all let's open this PNG file, and we can see here the training result, the loss is going down, which is a very good result. We can also, this is the loss, let's see the precision, the metrics of the precision. This should go up to between 0 and 1. We can see that this as well goes up, a very good results. Let's also open one of the validation batches. For example, this one is trying to predict images from batch number 1 at the validation images, and as you can see, he predict this one, this dog, as a Staffordshire Battle Terrier. I'm not familiar with all the breeds, but it seems that it, for each of the dogs, gave a prediction with high accuracy. Let's try to open another one. Let's open this one. This seems like a golden retriever. And what else? This is a Shih Tzu. Yes, I believe that this is a Shih Tzu. So I think we got a very good results, and let's continue to the last step, which is testing our model. So we have two images, a Doberman, and this is a Shih Tzu dog, and we will try to predict those two images. Let's go to the last phase, which is running an inference and test our model. So we will start with creating a new Python file. Let's name it step number 6, predict.py. Let's load the relevant Python libraries. We will use Yolo, OpenCV, and OS. So this is our first image, this is the second image. Let's copy the path for this dog image, the black dog, and we will try to predict the breed of this specific dog. So this is the relative path for the image. Now let's load the image using the imread OpenCV function. So the img variable contains our image, and now let's extract the dimension of the image, the height and the width. Now let's run the prediction. So we will load our model. Let's copy the model path, the full model path for our previous Python code. So it's under the dataset, and inside the dataset it's under nano model. This is the subdirectory, and the file name is of course we have to add the weight subfolder, and the file name is best.pt. So this is the full path, and now we are loading the Yolo model into the model variable. Let's define a threshold of 30%, and now we will run the prediction, sending our image to our model. So all the results will be stored in the results variable, and we will run a for loop. We will iterate through all the results, all the object discovered in this prediction. from each result we will get the bounding box x1, y1, x2, y2, the scoring, and the class ID. So if the scoring is above our threshold, then we will draw a rectangle around our object. We already grabbed the bounding box, the rectangle information. So we will use the rectangle function and put a rectangle around our discovered object. And then we will put the text with the name of our breed. So since we have the class ID from the prediction process, we have to convert it or get the class ID, the class name instead of class ID. So this is how we get the class name, and then we also put the text in those dimensions, as I said, 10 pixels above our rectangle. We also choose a font, how thick is the text, and the color of the text. Let's, for example, choose a green color for the rectangle and for the text as well. And then we display our image, and we will wait for a key to be pressed. So let's run it. As you can see, this dog was detected as a Doberman. Let's try the second image. Let's see if it's also predicting well our second image. As you can see, we add the path for our second image named dory.jpg, and the Doberman will be taken out. Let's run it again, the same code. Now, as you can see, it was detected as a Shih Tzu. I believe that the green color is not good. Let's change it to black, both the rectangle and the text, the label. Now it's better. Let's make the rectangle more thick. So we change it from 1 to 3. Let's run it again. Oh, now it's better. So thank you very much. I hope you enjoyed this tutorial. You are most welcome to subscribe my channel. Bye bye.